So let's take a look at this same unit exam that I gave back a few semesters ago. So this is the answer key after that test. No surprises here. This actually is a fill in the blank section. Now, will these be the questions that I ask for on your unit exam this Thursday? I don't know. But for instance, when we're talking about a single, let's see, the term that describes the mass of a single formula unit, that is a formula mass. Remember, that's for ionic compounds. The term molar mass actually is the mass of 1 mole of anything, including molecules. We talked about sigma and pi bonds. Pi are the secondary bonds. Cation is the name for a positive ion. We talked about the octet or rare gas electron configuration is actually where an atom has lost electrons or gained electrons to get a ns2 np6 electron configuration. Resonance structures are where you have swung from a different atom. So basically they are structures that have the different pot of valence electrons, but they are distributed slightly differently, resonance structures. Ionic bond is where we have had a transfer of electrons, a measure of an atom's ability to hoard or attract electrons to itself when bonded to another atom. That's what we call electron affinity, was what I was after there. So if you're wanting to jot these down, or you want a copy of this, I can't give you a copy of it, but you can actually pause the I almost said DVD. You can pause the video and jot things down if you want to. And then there's going to be a section where you say, is this a compound? Is this an ionic or molecular compound? And remember, if it has a metal, okay, then it's ionic. Okay, if there are no metals, then it is molecular. So in the answer key here, I have a squiggly mark under all of the metals. So sodium is a metal, so that's ionic. There are no carbon, hydrogen, oxygen, and hydrogen are on nonmetals, so it's molecular. Hydrogen, sulfur, oxygen, nonmetals, molecular. Nitrogen, hydrogen, nonmetals, molecular. And down here I have a squiggle mark under iron. And so that's a metal, so that makes it ionic. On to the next page. So the next page we start in on our ionic compounds, and there are actually 3 sections related to ionic compounds. This first one is I give you the ions. Okay, so this is where you crisscross. So let's see if I can zoom in here. Remember we said that, so I give you actually the ion and the charge and the ion and the charge, and you have to crisscross. So the number of bariums we need is 1, and the number of nitrates we need is 2. So barium 1, nitrate 2. Then, of course, you can kind of see how this goes. Remember, for instance, here for C, if I need 3 hydroxide groups, I have to put OH in parentheses and a 3 outside. So this section is crisscrossing. What do we got next? So this section is where I give you the name and you have to write the formula. So there are 2 more sections. So here's the name and write the formula. So again, what I do is I would usually write the component ions. So now this first one right off the bat, it has 3 words, but of course it starts with the metal, it starts with the cation, and so here is the break. So magnesium, hydrogen carbonate. So hydrogen carbonate actually is the anion, and of course magnesium is your cation. I write the component ions. So here we have magnesium is, it's a 2A, so that means it's a +2. And here we have hydrogen carbonate. You're just going to have to memorize that's HCO3 with a -1 charge. I write those next to it, even though you don't have to for this section. I know a lot of you do too, just so now that you can crisscross. So the number of HCO3s I need is 2, and the number of Mgs I need is 1. So Here we have lead 2 fluoride, so of course that's Pb plus 2, and fluorine is a 7A, and it forms a -1 charge, and then we crisscross there. So I think those are all kind of self-explanatory. Again, will these be the ones that are on your test on Thursday? I don't know, not necessarily, but this is just kind of a review to remind you what we did. And then the last section on ionic compounds is this one, where you're given the formula and you have to give me the name. And you can see what I did in the answer key here. Again, I took the formula and I broke it out into its cation and anion, and then I named the cation and the anion. Now, did I have to do this section, breaking it out into its component ions? No, not necessarily, but to me then it just makes it, you know, easier to go ahead and write the name. Remember that on your test on Thursday you have a full 2 hours to take it, so feel free to, you know, linger and come back to ones if you're not sure how, you know, if you want to double check what you wrote. Sometimes these 3 sections actually can kind of help each other. I don't know if that makes sense, but you can get hints from one of the sections for a previous section. I guess I will remind you that things like copper actually is it's a transition metal, and it's not, what was it, zinc, cadmium, or silver. So you have to use Roman numerals in the name. This just happens to be, and I didn't talk much about this in lecture, this is kind of a reverse crisscross to see what the charge of the copper is. Actually, it's a copper 2. Now, if you get the wrong charge and at least just write Roman numerals copper 1, I would be fine with that. But you have to put Roman numerals. This right here, the iron, the FeS, again, if we kind of reverse, did I say that right? Well, reverse crisscross, but if we notice that the sulfur is always a -2, then the Fe here must be a +2 to make it neutral. I don't know if that makes sense. I hope it does. But you're going to have to at least use Roman numerals because iron requires Roman numerals. And remember that, I don't know why we kind of struggle with this, but just the one, let's see, here's the anion that just has one atom. It's the monoatomic anion. It ends in ID as in dog, E. Don't forget that. And here's an example of our oxygenated halogens. The 7A elements combine with oxygen 4 different ways. Of course, this is bromite, so kind of remember those. Get your flashcards out. Okay, so I think at the bottom of this, yep, at the bottom of this now, here's where now we start with Lewis structures. And I said that there would be one of these on there. This is where you have to come up with a pot of valence electrons for the structure I give. So for instance, CO, you need to look up carbon. Carbon is 4A, so it has 4 valence electrons. There's 1 carbon atom. Oxygen is 6A, so it has 6 valence electrons, and there's just 1 of those. So, of course, the sum or the pot then here is 10 valence electrons. So that's what I'm after. Down here, I have an example on this test of hydrogen, of course, is 1 electron. Sulfur is a 6A, so 6 electrons. Oxygen is also 6A, 3 times 6 electrons. And now this is an example where now that we have a -1, we have to kick in 1 extra electron just for the charge, and that makes our pot of valence electrons 26 electrons. This idea of coming up with the pot of valence electrons actually is in the first step of drawing a Lewis structure, which is coming up on the next page. Oops, let me go back. I think I missed a part. So here are the Lewis structures that a few semesters ago students had to draw. So you can see how I drew the Lewis structures in the answer key. I came up with the pot of valence electrons, and then I distributed them around the structure. Remember we talked in lab that the one that goes in the middle is the lowest electronegativity, lowest chi, okay? And then we distribute the other atoms from there. We can draw, notice here on my answer key, I didn't draw the preliminary Lewis structure and all that. But what I did make sure is that my central atom, which is carbon atom here had a complete octet. How do I say this? In my final Lewis structure. So these are the Lewis structures, like I said, that they drew a few semesters ago. The carbon dioxide here. Let me scroll on down. Here's my other two for that semester. Cl2CO. Now again, I think this would be the case. The Lewis structures that you're going to draw on your test, you're going to have a middle atom, and the middle atom is going to be the lowest electronegative. And see, the middle atom will never be hydrogen, and you're going to extend atoms from that. So kind of keep all that in mind. And then the last one was Cl2F2. Again, what's going to be in the middle? Well, the carbon has the lowest electronegative value of those three elements, carbon, chlorine, and fluorine. So we're going to put carbon in the middle, and we're going to have the fluorine, two fluorines and the two chlorines extending out. When I came up with my pot of valence electrons, there was 32. And remember, like we did in lab, if we count these electrons on the final Lewis structure, we have 32. So we have 8 plus 8 plus 8 plus 8. That's 32 electrons. And the carbon's happy, and all of those other atoms are happy too. Then on your test, you're going to have, won't be this Lewis structure, but it will be another Lewis structure where I give you, this Lewis structure is given, and I ask questions about it. So it'll be a little different for y'all, but so notice that I pointed to 3 different atoms, this nitrogen atom, that carbon atom, and that oxygen atom, and I asked questions about the orbital hybridization. So now remember, this is where you count sigma bonds and lone pair electrons. Sometimes there aren't any lone pair electrons. Lone pair dots. Okay, and this is where we had a 2, 3, and 4. And we said you go across the row, and the first one was what, SP, and was linear. The next one, SP2. Hope this is ringing some bells. And the last one, SP3. And so it kind of went from there. So, for instance, let's go ahead and look at C, pick on C, okay? So if you look at that oxygen atom, there's 1 sigma bond, 2 lone pair electrons. 1 plus 2 is 3. So then we can know it's sp2 orbital hybridized, and it's what, trigonal planar, bond angle 120. So I hope that's kind of ringing some bells. Okay, let's see, what else did I have? So that semester I asked for count the total electrons on the final Lewis structure. Each time there's a solid dash, that is a covalent bond, it's 2 electrons. Of course, the dot's a pair of electrons. Pi bonds, remember that every time you have a triple bond, that one of them is sigma and 2 are pi. And anytime you have a double bond, one of them is sigma and 1 is pi. So kind of keep that in mind. Okay, let's see. On to the calculator stuff. Now again, I think on your test it's a little bit different. I'm pretty sure on your test I'm just asking for the molar mass of several compounds. So the molar mass, what do? You can use the abbreviated way if you want, but you have to show all work to get your credit here. So you'll have a periodic table, and here is the decimal number for lithium, and I only need one of them because that's what the formula says. Decimal number for hydrogen times 1, decimal number for sulfur times 1, decimal number for oxygen times 4. And round it to 2 decimals, and we get, our calculator spits back 104.02, but don't forget units of molar mass are grams per mole. So I think you have a few of those. Now again, this is this semester, that was that semester. So I'm going to go ahead and make, I hope everybody's with me, this is not for extra credit this semester, because we definitely covered these in lecture. We covered them, was it Friday and Monday, or was it just Monday? But anyway, this is worth regular credit. You have to come up with the what the weight percent is for each element. The example I had was this iron 3 hydroxide. So I needed a weight percent for iron, a weight percent for oxygen, and a weight percent for hydrogen. So like I said in lecture, what I would suggest doing is coming up with what the whole weight is. Okay, and then in each of the cases I divide what the weight of the element is divided by the whole weight. Weight of the element divided by whole weight. And you guys had some homework like that recently. And this is one of those problems where actually you can check. This should be about, what, 100%. Okay. Let's see, on to the bottom of this page. And again, you know, this is this semester. This isn't last semester or a few semesters ago. This is where it's just normal credit. You're supposed to reduce the molecular formulas to make them into empirical formulas. Reduce where possible. If you can't reduce it, then you just rewrite it. So, for instance, we have C6H12O6. We can divide everything by all of those numbers by 6, can't we? So divide by 6, divide by 6, divide by 6, and we end up with C1H2O1. Water can't be reduced. Okay, this one, caffeine, it can be reduced, but the largest common denominator is just 2. So we divide everything by 2, and we get a 4, 5, 2, and 1 with regard to carbon, hydrogen, nitrogen, and oxygen. Okay, then on to the last page. And the last page is where we do our, again with calculators, the whole mass to moles and moles to mass. So don't let it throw you off when it says how many moles, when it says how many moles of CH3OH molecules are there in this mass. We are after moles, so we're not going to use Avogadro's number. We're not after molecules. So this is a grams to moles problem, or mass to moles problem. And so we can do it in, so let's see, mass to moles. And we can do it using the molar mass. So we have to show this work. Always show all of your work. And so we're going to have to come up with the molar mass of the compound. We take 1 times the decimal number for carbon, plus 4 times the decimal number for hydrogen, plus 1 times the decimal number for oxygen. We've got the molar mass. So now the term we start with is the mass we want to convert. And then the molar mass, we're going to have to use the flipped version, 1 mole over 32.04 grams. That was the molar mass. And then we're rounding according to, what, 3 sig figs. Let's see what I had on the next one. So for this one, I have, it says, what is the mass? So question mark mass of this many moles. And we can do that using the molar mass of the compound. So the molar mass of the compound is up here, 2 times the decimal number for sodium plus 1 times the decimal number for sulfur. There's the molar mass. So here's the work down here. We take, the first term is the moles that we want to convert. The second term is the molar mass, and no, we don't flip it. Notice that we don't flip it because we want moles to cancel, and they will cancel if we just go ahead and put 78.05 grams over 1 mole. So we're left with units of grams. It looks like we were allowed 4 significant figures. Very good. And in this one, notice I am going to use Avogadro's number, so let's take a look. It says how many Fe2O3 formula units are there in this mass of the compound. So here I have a hint: 1 mole of formula units is equal to 6.022 times 10 to the 23rd formula units. So this is one of those where we're going to go from mass to moles, using what? The molar mass. And then we're going to go from moles to formula units using Avogadro's number. So this is what that looks like. Our first term is the mass, what we want to convert. Up here, I went ahead and showed the work of knocking out the molar mass of the compound. And so notice that here for the molar mass, we're going to use the flipped version, so grams will cancel, be left with moles. Now here's how we use Avogadro's number, and we want moles to cancel, excuse me, so put moles on the bottom and 6.022 times 10 to the 23rd formula units on the top. So multiplying it out, and we get, rounded to two significant figures, we get 5.7 times 10 to the 21st formula units. So I hope that all was helpful.